All right, in this video, we're going to take a look at calculating the equation of the least squares regression line using some summary statistics instead of some of the other ways that we've learned, like putting data into a graphing calculator or using the Minitab output. So what we already know about the least squares regression line is that the form of it is y hat equals a plus bx. So y hat, if you remember, that is the predicted response. So that represents predicted values for our response variable. X represents our explanatory variable. And in this form, A here is representing the y-intercept of our line, and B, the coefficient of X, that is representing the slope of our line. So one of the ways that we can calculate this y-intercept and slope is to use the summary statistics for X and the summary statistics for Y. So in order to do that, we'll need to kind of recall some old, knowledge about how to write an equation of a line. And we can do so if we have the slope and one point that exists on the line. So there's a couple facts here to know that'll help us, approach that. So one fact to know is that every least squares regression line that you ever calculate will always pass through or contain the point x bar, y bar. So what I mean there is if we have a scatter plot, and through that scatter plot we have a least squares regression line, well, if we were to find the mean of all of the x values from our data set and the mean of all of our y values from the data set, and treat that like an ordered pair, x bar, y bar, that point is guaranteed to be on the least squares regression line. So when we're looking for a point to plug in to to get us our equation, we can always pick the mean of x and the mean of y as a pair. Now the slope we can calculate using this formula, which is given on your formula sheet in AP Statistics. The slope B can be calculated by taking R, your correlation, times the standard deviation of y over the standard deviation of x. So let's see an example of writing a least squares regression line using these summary statistics. So a trucking company wants to create a mathematical model to help them with scheduling truck drivers to its delivery jobs. And the company has gone through the current month's jobs, and they have calculated the summary statistics on a couple of measures. And the company is wishing to use the distance of its deliveries to help predict driver hours needed. So they can, plug in a number and say, oh, this next delivery takes 75 miles. How many hours will I need to schedule a driver for to get that, to make that delivery? So going back through their current month's jobs, they have the summary statistics here for the distances of all the deliveries that they made. So the average distance was just under 80 miles, and distances varied by about 62.7 miles from the mean on average. The shortest delivery was 25 miles, the median was 60 miles, and the maximum distance was 210 miles, for example. And Y, the response, that's representing the driver hours that were needed to complete that job. So on average, the deliveries were made in 2.36 hours. Deliveries varied by about 1.9 hours. The fastest delivery was 0.75 hours, so 45 minutes, and the longest delivery took 6 hours. And we have this correlation here showing a fairly strong positive correlation between distance and driver hours, and the R squared value is given here as well. So let's highlight the things that we're going to need. So we're going to need one point that is on the line. And as we said before, the line of best fit, the least squares regression line, will pass through this ordered pair, the mean of x and the mean of y. So here is giving us x bar, the mean of x, and here it's giving us the mean of y. And the other thing that we'll need to calculate the slope, we're going to need the standard deviation of y, which is 1.89, the standard deviation of x, which is 62.72, and we'll need the correlation r. So here's our sx, and here's our sy that we can use in that formula. Now, just to be clear here, there is nothing standard about this output. So it's not like the Minitab output where everything was standardized and you can find it, the information always in the same place. This is just a table giving you summary statistics. So don't go by looking at the structure of the table. Go by thinking about where's my X bar, where's my Y bar, where's SX, where's SY, where's R, because those are the things you need. All right, so let's start by finding the slope. So the slope, B, we'll calculate that by taking the correlation R times the standard deviation of Y over the standard deviation of X. So let's plug in the values that we have. The correlation R is 0.718. The standard deviation of Y is 1.89 divided by the standard deviation of X, which is 62.72. So we'll go ahead and evaluate that on a calculator. So 0.718 times 1.89 divided by 62.72. And so there's our slope, about 0.0216. 0.0216. So that'll be our slope. So that'll mean that for each additional mile of delivery, we need to schedule 0.02 more driver hours to make that delivery. Now that we have the slope, we can calculate our, we can calculate the y-intercept using our equation structure. So y hat equals a plus bx. So we'll substitute in the things that we know in order to solve. We want to solve for that variable a. So we need to put in a value for y hat. That is a y value that is on the line. The mean of y is guaranteed to be on that line. So we're going to plug in the mean of y in place of y hat. We're going to leave a as just a because that's what we're solving for. We don't know what that is. Plus the slope, b, well, we just calculated the slope as being 0.0216. And in place of x, we'll have to plug in the mean of x, which is 79.4. So here we're just using the fact that this line will pass through x bar, y bar. All right, now we're just doing some algebra here. So we'll evaluate that 0.0216 times 79.4. So 2.36 equals a plus 1.715. And then we'll subtract that 1.715 from each side. And that will solve us for our y-intercept. So 2.36 minus 1.715 gives us a y-intercept of 0.645. Which would mean if the delivery was a distance of 0 miles, it would take about 0.64 hours to complete that delivery. And that might be accounting for things, the non-driving part of delivery, like maybe loading or unloading the trucks or things like that. So now let's put our equation together. We have our y-intercept A, we have our slope B. So here is our equation, here is our model. The predicted driver hours is equal to our y-intercept, 0.645, plus our slope, 0.0216, times our explanatory variable, which is distance. So from those summary statistics of distance and time, now we have an equation where the company can plug in a distance to predict how many hours they're going to need to make that delivery. Now, the back side of this has an example. So if you've got that handout, go ahead and pause the video and work through the back side of this. See if you can do this on your own. And then when you're ready, press play, and we will walk through it here together. All right, hopefully you are ready to go with your answers, and we'll check and see how you did. So on this example, we are looking at the relationship between runs scored and runs allowed. are the number of runs scored related to the number of runs allowed for MLB teams. So this table here is summarizing the statistics from the 30 MLB teams during the 2021 Major League season. So runs scored, that shows how many runs the team themselves are scoring. So on average, MLB teams are scoring 733.67 runs throughout the season. And that varies from team to team by about 70.24 on average. The lowest number of runs scored was 609 that year. The maximum was 863. Runs allowed refers to how many runs each team allowed their opponent to score against them, which has the same average, 733.67. That's just kind of the nature of runs scored and runs allowed. That will not always equal each other. In this case, it just does. And runs allowed have a little bit more variability, 91.8 runs variation from the mean on average. The least amount of runs allowed was 561. The max was 956. There is a moderate correlation, a negative correlation between runs scored and runs allowed. So teams that score more runs tend to allow fewer runs, and teams that allow more runs tend to score fewer runs. So that's just kind of a little bit of background about what these numbers mean, especially if you're not a baseball fan. So first, we're going to write the equation of the regression line using these summary statistics. So let's identify the things that we need. One thing we're going to need is a point on the regression line, and that point will be the mean of x and the mean of y. So here's the mean of x, and here is the mean of y. To calculate our slope, the three things we need are correlation r, the standard deviation of y, and the standard deviation of x. So 70.24, there's our standard deviation of x. 91.8, there's our standard deviation of y. So again, we'll start with the slope. So b, the slope, is equal to our correlation, negative 0.560, times our standard deviation of y on top here, 91.80, over the standard deviation of x, 70.24. So let's go ahead and evaluate that on a calculator. So negative 0.560 times 91.80 divided by 70.24, negatives 0.732, negative 0.732. So for each additional run a team scores, they're typically giving up about 0.73 fewer runs. All right, to find our y-intercept, well, we're solving here for a. So plugging in a value for y hat that is on the line, we're going to plug in the mean of y, which is 733.67. A, we're trying to solve for that. We're going to leave that as a variable. Plus b, you know what, our slope is negative, so let's make that minus 0.732 times the mean of x, which is 733.67. So 733.67 is equal to a minus, let's evaluate that, negative 0.732 times 733.67. So minus 537.05. We'll just add that over here to the other side to solve for a. 537.05. So 733.67 plus 537.05. We've got a y-intercept of 1,270.72. So putting that into our context here, the predicted runs allowed is equal to our y-intercept, 1,270.72, minus 0.732 times the runs scored. And that is our least squares regression line equation. So for B, let's interpret the slope here in context. The slope is a rate of change, so that shows for each additional unit of x, how the units of y are predicted to change. So in this case, that means for each additional run scored, the predicted runs allowed. Since this slope is negative, an increase of runs scored corresponds to a decrease of runs allowed by about negative 0.732. Now, does our y-intercept have meaning? Well, looking at the minimum here, the minimum run scored was 609. So the y-intercept is going to be a prediction with 0 runs scored, which is way lower than any MLB team would ever have. No MLB team would ever just go the whole season without ever scoring a run. So I would say here that no, it's not. The y-intercept would mean that a team that scores 0 runs would be predicted to allow 1,270 runs over the course of the season. It does not make sense for a team to score 0 runs. So for D, the Seattle Mariners scored 697 runs. How many runs allowed does the model predict that the Mariners would have? All right, well, let's go ahead and substitute that in. So our equation, runs scored, we're just taking that 697, and that's being substituted in here for runs scored. So runs allowed is going to equal 1,270.72 minus 0.732 times the 697 runs that the Mariners scored that year. So let's evaluate that. 1,270.72 minus 0.732 times 697. That predicts the Mariners would have allowed 760.516 runs allowed. And lastly, would it be reasonable to use this model to predict the number of runs allowed for a team that scored 420 runs? Well, whenever you're kind of thinking, is it reasonable to make this prediction, you need to think about if you are extrapolating or not. Extrapolating means using a value for our explanatory variable that is outside of the boundaries that we actually studied. So looking at the table here, let's check out runs allowed. Well, the minimum was 609, and 420 runs is going to fall well below that. So this model would be extrapolating, and that would not be a good idea to use this model. You know, it's really trustworthy between 609 and 863 runs scored. 420 is just well outside that. So we'll say no. The minimum runs scored was 609. 420 runs scored is well below that amount. So using the model to predict runs allowed would be extrapolating. And just a comment on extrapolating. Extrapolating would produce untrustworthy estimates. Now notice something that I'm using a lot here in this response is I'm using context. It's always a good idea in AP statistics to write in context as much as you can. So I'm talking about the minimum runs scored, and that was 609. So 420 runs scored is well below that amount. So using this model to predict runs allowed would be extrapolating. Definitely throw that context in there as much as you can.